We'll start dimensional analysis. Now the first question arises, what do you mean by dimension? So dimension, there are two types of physical quantity, fundamental quantity and derived quantity. Now what are fundamental quantity? In SI unit, mass, length and time, not only three, total 7 fundamentals are there. So can you name it please? Mass, length, time, temperature, current, mole, amount of substance, luminous intensity. So 7 fundamentals and 2 auxiliary unit, supplementary you can say, that is radian and S2 radian. So 7 fundamental plus 2 supplementary, total 9. That will cover the whole entire physics. You can express any physical quantity with the help of these all 7 plus 2, 9 fundamental quantities. So fundamental means you cannot derive one from the other, like mass, length, time. Just see the example. So you cannot derive anything from length, you cannot derive mass from length. You cannot derive length from mass. You cannot derive expression for time from mass. Similarly, so these are called fundamental. These are called fundamental quantity. And with the help of these 7 fundamental, you can get a number of physical quantity that are called derived physical quantity. Derived physical quantity. As for example, area, volume, speed, velocity, acceleration, force, these all are derived physical quantity. So a number of physical quantity can be represented in terms of MLT, mass, length and time. And then for representing few more physical quantity, you need temperature also, you need luminous intensity, you need mole concept, mole, amount of substance, and then ampere also, current. Okay. But most of them will be within the 3, mass, length and time. So we are discussing what is dimension. So what is dimension? What is dimension? Okay. So how will you define it? Dimensions of a physical quantity, dimensions of a physical quantity are the powers, or exponent, are the powers which are raised on fundamental quantity to get derived quantity, derived physical quantity. So that power is called dimension, powers. So as for example, if you want to express area, so area is L square. That is 2, dimension of area is 2 in length. If you want to represent volume, what is the dimension of volume? So this is L cube. So 3 in length. So similarly you can write the dimension of, say, very fundamental quantity, that is density. Density is mass by volume. So this is mass by volume. So mass is m and volume is L cube. So you can write this is ml minus 3. So 1 in mass minus 3 in length, or you may write this one as m L naught L naught means 1. L raised to 0 means 1. M L raised to 0. No. M L raised to minus 3. L raised to minus 3. And then T raised to 0. You can add T also. But then you have to put raised to 0. So it is independent of T. Time part is not involved. So M L minus 3. So what are the dimension of density? 1, minus 3, 0 in mass, length and time respectively. So we used to write dimension. If somebody asks you what is the dimension of density, your answer should not be M L minus 3 T raised to 0. It means you are telling dimensional formula. So dimensional formula and dimensions. Remember, dimensions are the powers, exponent. So these you have to state about this power. So power is 1, minus 3, 0. These are called dimension. So dimension of density. क्या है? R 1, minus 3 and 0 in mass, length and time respectively. You have to write like this. So these are the dimensions. And if I ask you what is the dimensional formula of density, then your answer is M L raised to minus 3 T raised to 0. Within that bracket is called dimensional formula. And if you represent density, suppose by a quantity D, then D is equal to this. So this is called dimensional equation. This is called dimensional equation. If you represent density by D, then D equals to M L minus 3 T raised to 0. So this is called dimensional equation. Dimensional equation. Dimensional equation. And this one alone is called dimensional formula. Dimensional formula. Okay. Now take the snapshot. Taken? Yeah? Someone taken? Okay. Now talking about moving towards the dimension of some more physical quantity, that is volume, density and then speed. Let me talk about the speed. The speed and velocity have same dimensional formula, same, because whether it is speed, whether it is velocity or relative velocity or any velocity, that velocity has the same dimension. So this is equal to distance by time. So distance has L T minus 1. If you want to add M, you can add L T minus 1. No problem. So this is the dimensional formula of speed or velocity. Speed or velocity. So whether it is velocity of light, whether it is velocity of an object, all relative velocity all have the same dimension. That is M raised to 0, L raised to 1, T raised to minus 1. Then acceleration. Acceleration. So how will you find the dimension of acceleration? This is rate of change of velocity. So L T minus 1 is for velocity, that is change in velocity. So whether you are talking about change in velocity or velocity, they have the same dimension. They have same dimension. Change in velocity or velocity. So velocity minus velocity, that is called change. So unit is velocity only. So LT minus 1 divided by T. So rate of change of velocity. So this is LT minus 2. This is the dimensional formula of that acceleration. Then coming towards force. Force is, you can write the unit also. This is meter per second. Acceleration is change in velocity by time. So change in velocity has dimension same as that of velocity. So what is change in velocity? Velocity, final velocity minus initial velocity. So you are subtracting to velocity, so you are getting velocity only. Then what is the dimension of velocity? Dimension of velocity is Lt minus 1. So write down the dimension of velocity. Lt minus 1 divided by t. Because change in velocity by time. T for time. L for length, M for mass. MLT. Remember, M for mass, L for length, T for time. Then this is L and then T raised to minus 1. 1 minus 1 is already there. So it is T raised to minus 2. Now force, which is mass into acceleration. Okay, this formula you know from class 9 onwards. Newton's laws of motion. Force is equal to mass into acceleration. So any force, whether it is a tension force or this force, they have all same dimension, that is mass into acceleration. So centripetal force, same acceleration, same dimension, that is mass is m and a is Lt minus 2. You can write the unit also, kg meter per second square. So what is the unit of kg meter per second square? What is the unit of acceleration? That is meter per second square. What is the unit of speed? That is meter per second. Meter per second. You can write the unit also. Just observing the dimension formula, you can able to write the unit also. SI unit. Okay. Now talking about force and then momentum. So momentum, these are the physical quantity which you have already studied from class 9-10 onwards. So momentum. So what is momentum? Mass into velocity. So mass is capital M and then V means velocity, which is Lt minus 1. Lt minus 1 is the dimension formula of momentum. Once you know the momentum, the another term is impulse. Impulse is nothing but change in momentum. Change in momentum. So we will learn each term in the chapter, coming chapter, like Newton's laws of motion. One unit is there in class 11. There we will learn about what is impulse. So when a very large force acts on a body for a very short period of time, the combined effect of force and time is called impulse. So when a batsman hits a ball, so he applies a large force for a very short interval of time. So the combined effect of force and time, that is force into time, this gives you impulse. So I am writing the formula only. So impulse is equal to force into time. Now you know force is change in momentum, mb minus mu by t into this t, time. So this t will cancel out. So what you get? Change in momentum. So change in momentum is equal to the impulse. So what should be the dimension of impulse? The dimension of impulse should be same as that of momentum because it is change in momentum. So whatever is the dimension of momentum, that is the dimension of change in momentum. So this is equal to mlt minus 1. Okay. Now you can write the unit of impulse also, Newton second. Or you can write the unit in kg meter per second also. Kg meter per second. This unit is kg meter per second, also known as Newton second. Newton second, NS. And for Newton, force, second for time. Force into time. Now, impulse and then work done. Work done. You know, work done is force into displacement. Okay? Fs cos theta. Now, cos theta is a number. For any value of theta, cos theta will give you a number. And number has no dimension. If I ask you what is the dimension of 1, 2, 3, 4, all dimensionless. What is the dimension of constant pi? Dimensionless. But there are some physical quantity which is a constant and has no dimension. But at the same time, there are another physical quantity which are also constant but it has dimension. As for example, gravitational constant. It is not a dimensionless constant. Planck's constant. It is not a dimensionless constant. Okay, we will discuss one by one. So work done is force into displacement. So force, dimension of force we have already written mlt minus 2 divided into this S means length. So you are getting ml square T minus 2, ml square T minus 2. So what should be the unit of work done? Unit is kg meter square per second square, also known as force Newton meter. This is equivalent to Newton meter, and Newton meter is nothing but joule. 1 joule, Joule. This is 1 joule. Okay. Now energy, any form of energy. Energy is what? Work done. So energy, whether it is kinetic energy, potential energy, heat energy, all electrostatic energy, all energy have the same dimension. That is joule is the unit. So energy is work done, and work is ml square T minus 2. So what you are observing, simply by changing the power of mlt, the different physical, derived physical quantities can be represented. So with the help of only 3 mlt, you are simply changing the powers, and the physical quantity itself is going to be changed. So by changing the powers, you can represent any physical quantity. Okay, take the snapshot. I will show you some more physical quantities. Taken. Now, what is the dimensional formula of acceleration due to gravity? So whether it is a normal acceleration or acceleration due to gravity, both have the same dimension, that is Lt minus 2. Same unit, meter per second square. So what is the value for small g? 9.8 meter per square. Average value is 9.8 meter per second square. So see the unit. So now we are representing some more physical quantity. So now the physical quantity we are going to represent is the force impulse. Pressure is force by area, actually total normal force. That is called thrust, divided by area, per unit area. Total normal force acting per unit area is defined as force. So thrust by area is called pressure. So force, any force has same dimension. So T minus 2 for force, and area is L square. So then how to write this one? That is m L, see, L raised to minus 2, L raised to 1. So this is L raised to minus 1, T raised to minus 2. And what should be the unit of pressure? Unit of pressure is Newton per meter square. So this is known as Pascal. Pascal. PSCL. Pascal. Pa. Okay? Unit. Side by side I am talking about unit also. Now once you know pressure, then stress, one physical quantity is a stress. A stress is again force by area, but the force is deforming force. Deforming force acting per unit cross sectional area. Acting per unit cross sectional area. So okay, anyhow it is force by area. So whether the force is deforming or tension, so force by area. Area means whole surface area, maybe cross sectional area, but dimension will be same. So again we have the same dimension formula, ml minus 1 T minus 2. So remember, pressure and stress are the physical quantity which have same dimensional formula, ml minus 1 T minus 2. Then we are talking about the next physical quantity, that is universal gravitational constant. Universal gravitational constant. Gravitational constant. Sometimes we talk about a constant should not have any dimension. Okay, I agree. 1, 2, 3, sine pi, sine theta, sine 60 degree. These quantity have no dimension. Okay, angle, it has no dimension. But here is physical quantity, though it's constant. Like pi is also a constant, but pi has no dimension. But this is a universal gravitational constant represented by capital G. And this is a quantity which has got the dimension, though it is a constant, but it has dimension. Why? Because we know gravitational force between two bodies, G into m1 m2 by r square. So r is the distance between the center of two bodies. Center of two bodies, center to center distance, separation is r. So this is G m1 m2. So you have to find G. So what is G? So let us first write the formula. F into r square by m1 into m2. This formula you have studied in class 9 standard, if you can recall your memory. Yeah? Am I right? Newton's law of gravitation is there. So force is ml t minus 2, then r, any distance is L square. So whether it is radius or distance or anything, r is L square. m1 m2, mass into mass. Okay, one mass you can cancel. And then finally you are getting m raised to minus 1 L cube. See, t raised to minus 2 is the dimensional formula of gravitational constant G. Written? Yeah? Now the another factor is Planck's constant. Planck's constant. You know, Max Planck, photon. Photon is, what is photon? Tiny packets of energy. And each packet contains energy equal to h nu. Nu is the frequency of radiation. This h is Planck's constant. Where h is Planck's constant. Where h is Planck's constant. Where light is assumed to be the flow of photon. Now photon, what are photons? Photons are tiny packets of energy. And each packet contains energy equal to h into nu. H is the Planck's constant. So, and nu is the frequency of radiation. Frequency of radiation or light. Okay. Frequency of radiation. So, what is h? Energy of photon. This E is for energy by nu. So, energy, any energy is work done. And work done has dimension. Yeah, you have already written ml square t minus 2. Am I right? This is the dimensional formula of energy divided by frequency is actually 1 by time period. Reciprocal of time period is called frequency. So what should be the dimension of frequency? That is t raised to minus 1. So write here t raised to minus 1. Okay. Then finally you can adjust it. This is m l raised to 2 and then t raised to minus 2 and then minus plus 1. This is minus 1. Am I right? Just check it. Check it. Am I right? Energy is ml square t minus 2 divided by frequency is t raised to minus 1. You just check it in the numerator. Now it is ml square and this will become plus 1 minus 2 plus 1. This is minus 1. So ml square t minus 1 is for Planck's constant. Remember, these are the constants which is having dimension. Now this quantity, these quantities are constants, but they have the dimension. They are not dimensionless constant. Okay? But remember, pi, 1, 2, 3, these are dimensionless constant. Dimensionless constant. Okay. Now take the snapshot, I will rub it. Take it. Now some more physical quantities I would like to mention here. That is moment of inertia. or before that, okay, moment of inertia. Remember, this is ml square. So dimension of moment of inertia, actually it is mr square, mass into, so if you have a mass m and is rotating about this axis, whose distance from the axis is, perpendicular distance is r, then the energy of this mass which is rotating about this axis is mr square, is mr square. So mass into square of the perpendicular distance between the body and the axis. So okay, from where this formula comes, I will tell you in the chapter Rotational Dynamics. I think it is 5th unit. I will discuss it there. So mr square, just remember it. So this is m, and then r is, any distance is l, so ml square is moment of inertia. Now I am talking about another term, torque. Torque, which is moment of force. And moment of force is nothing, torque is equal to force into perpendicular distance between the line of action of force from the axis of rotation. So if that perpendicular distance is d, perpendicular distance, F into d is called torque. So force is ml t minus 2, and then d distance, d is distance only. So this is ml square t minus 2. So this is the dimension formula of torque. Now angular momentum, linear momentum and angular momentum. If a particle rotates about some axis, then it will have momentum, and that momentum is called angular momentum. And if it is going in a straight line, then the momentum possessed by the body is called linear momentum. So angular momentum is equal to mv into r. Say this particle, velocity of the particle in circular motion is always about along the tangent. So momentum is mv, and then take the perpendicular distance of mv from this point, r. So mv into r is called angular momentum, or p into r. If you represent momentum by p, then p into r, or p into d, you can take d also, where r is the perpendicular distance of the line of action of momentum from the axis of rotation. So you have to consider the perpendicular distance. So momentum is mass m, then v is lt minus 1, and then r is l. So this is ml square t minus 1. We will learn each and every physical quantity which we are mentioning here in the next chapter. Okay, you will study all the physical quantity in detail in respective chapters. But from this beginning dimensional analysis, you have to know some physical quantity. How can I write the dimension of that physical quantity? Provided that if you know the formula, you can write the dimension very easily. Okay, now we are talking about some more physical quantity. Okay, take the snapshot. Taken. Okay. Now, like coefficient of viscosity. So, coefficient of viscosity denoted by a symbol eta. Read as eta, Greek symbol eta. So this eta is nothing but I am giving you the formula force, viscous force F is equal to 6 pi eta r v. So actually this formula comes in the chapter viscosity, fluid dynamics. Fluid dynamics is one of the chapter, and there we will study about this viscous drag force, eta coefficient of viscosity, r radius of the spherical body falling through a fluid column. If you have a container containing some fluid and a spherical object, so this is a spherical object of radius r. Now it is moving, falling inside the fluid column with a velocity v. Then force acting, viscous drag force acting on the body, that spherical body is 6 pi eta rv. Eta is the coefficient of viscosity of this liquid, r radius, v velocity, and f is the viscous drag force, nothing but liquid friction, fluid friction. And fluid is nothing with something which can flow. Air is the fluid, water is the fluid, something which can flow. Okay, so when you allow this spherical ball to sink or to move inside the liquid column, and suppose the velocity of the liquid, that spherical ball is v at any instant, then viscous force F is given by 6 pi, it is a constant, eta r v. From this formula you can find what is the dimension of eta. So eta is equal to F by 6 pi r v. Remember, 6 pi will have no dimension because 6 is a number, and such a number which is a constant and has no dimension. Pi, this is also a constant, dimensionless constant, it has no dimension. So then F by rv. So the dimension of F is ml t minus 2, and then r is L and v is L t minus 1. So what you get? So this is m, you can cancel one L from numerator and denominator, and then m L minus 1, then t raised to, what is t raised to? Minus 1. So just observe, coefficient of viscosity, is there anything, any physical quantity which has exactly the same dimension? Yeah? Angular momentum, see the angular momentum? Angular momentum and Planck's constant. See, angular momentum and Planck's constant, are they have same dimension? Yeah. So there are some physical quantity which have same dimension, but their nature, quality, properties will be different. Okay? So ml minus 1, t minus 1 is the coefficient of viscosity, eta. Now there are some more physical quantity like coefficient of elasticity, coefficient of elasticity. Coefficient of elasticity, properties of solid, elasticity. So denoted by Y, or then Y is equal to a stress by strain, a stress by strain, and a stress has dimension same as that of pressure, because a stress is also the forming force per unit cross sectional area. So what was the dimension of pressure? Pressure is force by area. So force by area into a strain has no dimension. A strain, I am writing here, a strain is nothing but change in dimension per unit original dimension, or you may say delta L, change in length by original length. So length by length, so it has no dimension, no unit also. So because numerator and denominator has same thing, length, length, then it has no unit as well as no dimension. So stress, so whatever is the dimension of a stress, that will be the dimension of coefficient of elasticity. Strain has no dimension. So then force ml t minus 2 divided by area is L square. So this is ml minus 1, 1 L will cancel out. So ml raised to minus 1, t raised to minus 2 is the unit of coefficient of elasticity. Remember, coefficient of elasticity, stress, they have the same dimension. Pressure, they have the same dimension. Pressure, same dimension. Now, talking about some more physical quantity like angular velocity. Angular velocity. Just take the snapshot. Yeah, taken? Okay, okay. So, angular velocity, d theta by dt, d theta by dt. So, we are talking about angular velocity. So, angular velocity denoted by omega and is d theta by dt or delta theta by delta t, average angular. But instantaneous is d theta by dt. Okay. So, theta has no dimension. Why? Because theta is equal to L by R. But it has unit. There are some physical quantity which may not have dimension but have units. Like angle. Angle has unit. If it is a plane angle, then it will be measured in radian. And if it is solid angle, then it will be measured in ST radian, denoted by SR. So it is a plane angle. So then theta should have unit, which is radian, but it is a dimensionless quantity because numerator and denominator has the physical quantity which is of same nature, length, radius, length by length. So it has no dimension. So this is dimensionless. Then 1 by then t for time. So this is t raised to minus 1 is the dimension of angular velocity. Now we are talking about angular acceleration. Angular acceleration. So angular acceleration is the rate of change of angular velocity, that is d omega by dt. Okay. Now what is the dimension of omega? Omega is t raised to minus 1 divided by again t. So it is t raised to minus 2. Remember, angular velocity has unit. So unit is radian per second. And angular acceleration has also unit. That is radian per second square. Radian per second square. Unit. Unit. Then angular acceleration. Now, velocity of light that you all know. Velocity gradient. Velocity gradient. Velocity gradient is nothing but velocity by time, distance. Velocity by distance. This is called gradient. So velocity, dimension of velocity is Lt minus 1 by L. So this is T minus 1 only. L will cancel out. So this is velocity gradient. M naught L naught T raised to minus 1. See, velocity gradient and frequency has same dimension. If you want to write the dimension of frequency, time period t, then frequency is 1 by time period, and time period is 1 by t. This is t, then time period has dimension 1 by t minus 1. So frequency and velocity gradient have the same dimension. Same dimension. Okay? But the other physical quantity, like that we will study one by one, kinetic energy, potential energy, they all are energy, and energy have the same dimension. So we are writing about kinetic energy, kinetic energy, kinetic energy. You know the expression is half mv square. Yeah, you know it from class 9 onwards. So this is half has no dimension, m. Then what is v square? V is Lt minus 1. So Lt minus 1 whole square. So this is m L square T minus 2 is the dimension of kinetic energy. Unit is joule only. So think about potential energy. Now potential energy should have also same dimension, which is mgh. So m and g, what is the dimension of g? This is acceleration. So Lt minus 2, acceleration, meter per second square. into H, again L. So what you get? That is m L square T minus 2. So whether it is kinetic energy, potential energy or energy have same dimension. And this is similar to that of work done. Work done is also having same dimension, ml square T minus 2. Yeah? Am I clear to you? So then potential. Now we can talk about some other physical quantities also. That is rotational kinetic energy. Rotational kinetic energy. Take the snapshot. I will take few minutes more. Okay. Second. Now linear kinetic energy we have seen half mv square. Rotational kinetic energy. Rotational. So again it is energy. So again this have the same dimension. Rotational kinetic energy. The formula is half I omega square. Remember, when a particle rotates about some axis, then the energy possessed by the particle is called rotational kinetic energy, and is half I omega square. I for moment of inertia. I for moment of inertia. We have written earlier. So this I for moment of inertia. Moment of inertia. And has dimension, remember, ml square. So write the dimension of I, which is ml square, and then what is the dimension of omega? Omega is d theta by dt. D theta has no dimension. dt means t, 1 by t, that is t raised to minus 1. So this is t raised to minus 1 square. Square it. So what you get? ml square t minus 2. See, whether it is rotational kinetic energy, whether it is kinetic energy, whether linear kinetic energy, whether it is potential energy, all have same dimension. All have same dimension. Even heat energy, same dimension. Okay. Now, there are a number of physical quantity, but doing all these physical quantities is not possible here. So, you just remember all this physical quantity. You will study one by one. Some of the physical quantity you will study in class 12 standard, like potential, electric potential, electric potential. So how will you define it? Work done in bringing a unit charge. That is work done per unit charge. In bringing it from infinity to that point is called electric potential, and that electrostatic potential or electric potential is equal to W by Q. Now W is the work done. So ml square T minus 2. Force ml minus 2 into L, ml square T minus 2 divided by Q. Now charge is not the fundamental quantity. Remember, ampere is the fundamental, and current is equal to charge by time, flow of charge per unit time, charge by time, that is Q by T is current. So what is Q? Current into time. Now Q current, if current is represented by ampere A and T for time, then what should be the dimension of ml square, then T raised to minus 3 ampere raised to minus 1. Now earlier you are taking only 3 mlt. Now you are requiring one more additional ampere also. So when you study the heat chapter, there you need to take temperature also. Temperature is also required to write the dimension. So once you know the electric potential, you can find the resistance, dimension of resistance. So resistance is potential difference. Resistance R is V by I for current. Okay. So don't get confused that I is moment of inertia. Here I is for current. Okay. So there are a lot of physical quantity and symbols are limited. That's why we are using same symbol for representing different physical quantity. So don't get confused. So this is I, moment of inertia, and here the I is current. So this V is potential difference. So whatever is the dimension of potential, electric potential, the same is the dimension of potential difference. whatever is the dimension of velocity, the same is the dimension of change in velocity. So for V it is ml square t minus 3 then a raised to minus 1 divided by I for ampere. So write ampere here. Then now you are in a position to write the unit of dimension of R. So dimension of R is, yeah, dimension of resistance is equal to m L square t minus 3 and then a raised to minus 2. Yeah, minus 1. Minus is already there. So it is minus 2. So this is the dimension of resistance. You can write the dimension of resistivity. Resistivity. This you have also studied in class 10. So resistivity rho. Okay. So what is rho? R into A by L. Because R is equal to rho into L by A. So rho is equal to R into A by L. So resistance you got just now. So ml square t minus 3 then a raised to minus 2 divided by L, then area. This is area. Remember, this A is for area, this A is for ampere. So this A is for L square. L square is area divided by this L length. You can cancel one of the L and then finally you are getting, so m L raised to 3 t raised to minus 3 then a raised to minus 2. Am I right? Just check it. Just check. M L raised to 3 t raised to minus 3 a raised to minus 2. So this one you can write a dimensional formula of any physical quantity, provided that you should know the formula. Formula you have to know. And this physical quantity you will study in class 12 standard. Or class 10 standard also someone can study it. So the children who are coming from class 10, they may know what is R, what is rho, resistivity, what is electric potential. These quantities are well discussed in class 10 standard.